Today we'll talk about a high-order scheme for modeling viscous incompressible fluid flow in a channel with a step. The viscous incompressible fluid flow in a channel with a step is studied under steady-state conditions. The present work employs a fifth-order scheme using 13-point grid. The present scheme also uses fourth-order boundary conditions to further improve the accuracy of the results. Two well-known workshop problems are chosen for comparison of results: the problems of contraction and expansion flows. Our results compare favorably with the literature from experimental and numerical point of view. Regarding a brief introduction of the problem, the flow in a channel with a step is a classic benchmark problem in fluid dynamics, and it has been the subject of numerous studies. These problems involve expansion and contraction flows and pulsating inlet flow conditions in a channel. Contraction flows in a channel with a step has been a focus of considerable attention and a subject of a major international workshop, reference 15. Among the most prominent work on the subject, Boger, reference 9, provided a comprehensive review of the flows of viscoelastic fluids for both Newtonian and non-Newtonian fluid mechanics. His experiment data suggests the formation of a trailing edge vortex downstream of the step, which was also detected in the stream function and the plotted at selected values of R between 100 and 1000 by previous work by the author, where R is the Reynolds number. Other researchers include Dennis and Hudson, who were able to qualitatively detect the presence of this vortex through grid refinement. Hawkins et al. Reference 5 were able to visually detect the trailing edge vortex at Reynolds numbers 450. They obtained converged results up to Reynolds numbers 100 for the expansion case and Reynolds numbers 800 for the contraction case. In the present work, we used a fifth-order scheme to discretize the given partial differential equations. We also used a fourth-order vorticity function at the boundary. Let's get into the mathematical formulation of the problem. The Navier-Stokes equations, which will govern the fluid flow in the channel, is given by a coupled system of equations. The two equations have the psi and the vorticity functions, which is stream and the vorticity functions, and R is the Reynolds number. Equations 1 and 2 form a coupled system of equations. Figure shows a profile of the channel and some of the parameters involved. The boundary conditions are given by 3 through 7. where these boundaries are indicated relevant to the corresponding equations. So once we have examined the problem, we come to developing the numerical scheme. The first equation, which is equation 1, is very straightforward. Here, for the left-hand side, we can simply use sixth-order central difference approximations for the second partial derivatives of the stream function. Same thing can be done in the vorticity equation. The first part, or the Laplacian, again, that can be discretized by sixth-order central difference approximation. This is the highly nonlinear part, which is also known as the convective term. So for the convective term, we'll look into that specific development now. So first of all, the discretization of the vorticity equation is carried out using this 13-point grid, which is based on more like a central difference type of approach. So when we carry out the development, we have a numerical scheme, which is given by equation 8. Okay. So the coefficients are all indicated by cap A, and it's given subsequently right here. The vorticity equation development is shown here, the convective term, which is being discretized using this expansion, summation bi omega I. Now, bi omega I was used to write down the Taylor series expansions for each of the omega I term, which of course exclude the omega 0 that pertains to the main diagonal of the resulting coefficient matrix. So these are essentially the off-diagonal coefficients. And when we carried out the development, the resulting system of equations, which was actually an the resulting system of equation, which was actually an overdetermined system, that led to the following result given by 9. And the coefficients omega I in 9, they are given by following. So we used the notation now gammas to indicate the individual ones. So therefore the gamma 0, which pertains to the alpha 0, that is given right here. And then the off-diagonal ones are given by the remaining part in this 10. So as you can see here, all of these expressions involve alphas or alpha i's from 0 through 12. And we list them as follows. So alpha 0 is given by 11, which shows that this actually is a negative quantity. So the significance of alpha 0 being negative will be discussed very soon. So we have those 4 cases depending upon the signs of the first partial derivatives of stream function. Therefore, case 1, when both of them are positive. Case 2, psi x positive, psi y negative. Likewise, case 3 and case 4. So once we have those 4 cases, we can therefore use them to demonstrate that the ratio of the off-diagonal elements to the main diagonal element, which is alpha 0, and that ratio actually is the sum of the absolute values of the off-diagonal elements to that of the absolute value of the main diagonal, comes out to be 2.2. So this actually is, we called it this, just called it diagonal ratio, but this is actually a measure of the diagonal dominance of the system of equations. And this is really an important criteria. So if we examine that, a result from the linear algebra, which relates to the existence and uniqueness of the solution to the matrix equation Ax equal to B, that requires matrix A to have the diagonal dominance, negative elements on the main diagonal, and positive elements elsewhere, which means off diagonal elements to be positive. So that's how we have the main diagonal elements to be negative, which we showed in a second ago, the choice of alpha 0 right here, going back by 11. And then the diagonal ratio, which we try to achieve as large as possible, and we were able to get it 2.2. So that is desirable to be as large as possible, which has to do with the existence and uniqueness of the solution to 13. Okay. All right. So once we have the scheme, we can therefore substitute those alpha i's back and then get the coefficients of the discretized scheme. So therefore, those coefficients are given again by 4 cases in terms of gamma I, and then the final scheme is summarized as follows, 14. And those gamma i's are given by these 4 cases, right? So once we have obtained the scheme, it's a matter of some mathematical manipulation to show the order of the scheme to be 5th order. So this mathematical manipulation that I will not get into that detail is given here in 3.1 And if we follow it through, we just have to kind of, for now, look into the error term, which is OH5, because as you can see, after all that manipulation, what I have here is this result. So this is the convective part. Let me see if I can change the color here to maybe red for a second. So this is the convective term. And this is the Laplacian. So these together constitute the vorticity equation. And this is fifth order, because that's what we have shown here, that this OH5. So you can see that it involves those fifth order terms. Okay, so then boundary conditions of for the vorticity, those are done in a similar way. So I will not get into those details. We will therefore just look at some examples and comparisons. Okay, so some of the well-documented results which are given in the reference indicate how the present scheme shows superior convergence and better accuracy. So these are, as you can see, different parameters, and various cases are examined, various values of Reynolds number, and for various step size h. So then the comparisons are kind of discussed here. And in particular, those details that how the present scheme shows superior convergence and better accuracy, typical cases are indicated in the section 5, which is the conclusion. It is very, very specifically what cases were looked at. So, for example, for Reynolds numbers 10, 50, and 100 at step sizes indicated, we have some of the results. One of them is the fourth order scheme developed previously by the author. And then there is the Greenspan scheme, which is also a well-known result from the literature. So those details are all here. And I think now I will conclude my discussion. Thank you very much. Have a nice day.